Astrolabe is an open source project we have been working on to help folks map their murky clouds. So it is available on GitHub. The link is up here, or hit us up in the chat if it's easier to do that. But as we go forward, it's always kind of interesting to start with an origin story. So why did we need another open source tool? Why did we need another mapping tool? And so, like all good stories, it has a beginning. And our beginning was when Patrick and I were working at Life360, a relatively common story. Lots of growth, 50 to 100% growth year over year for multiple years on end. And things were breaking. And things were breaking in ways that they didn't make sense to us. So component A over here would break, and then component C over here would have issues. And we're like, what's the linkage there? And we had tools, New Relic initially, and then later Datadog. And we're like, okay, cool. Let's map it. You guys say you map this stuff. And they came back and they're like, we actually only map HTTP calls and a couple of other protocols. And we had our own custom async protocol. And this was basically distributed like a distributed RabbitMQ type thing. And they went totally blind. And so now all of a sudden, we would have had partial visibility into the environment and not anything we could make any decisions on. So Patrick and I, as I say here mostly, Patrick went and built a project called Itsy Bitsy that could spider across the infrastructure and map. And those maps would look something like this. Don't expect anybody to actually be able to read this, but this is an old version of part of Life360's environment. And that was actually super useful if you're an SRE and you knew how to interpret this. But it was very hard for non-SREs and people without that deep tribal knowledge to understand. So as we got back together about a year or so ago and started working on this, we wanted to go in and fix some of the weaknesses in that Itsy Bitsy implementation, but keep the good stuff. And so, some of the weaknesses that Itsy Bitsy has was all recursive discovery of servers. So go connect here, see where it connects, go to the next one, so forth and so on. And that was a tree-based relationship, but networks aren't really trees. And it didn't deal well with disconnected servers because it couldn't find them. There was no link to them. And then anytime there was a new relationship between service A is now using a new protocol or something, or new resource type, that required code modifications, under the covers, very slow. And over time, it just diverged from reality. But there was some good stuff, as I mentioned, that we want to keep. So it was agentless. We did not have to install a single bit of code on any server. It would just connect over SSH, run some commands, and pipe that information back. That was really good from a security standpoint. API, being able to call APIs of AWS or other infrastructure providers, Kubernetes, things like that. And then we weren't able to do this before, but we tweaked it a little bit. Manual inputs, we could actually put pieces into this. And the map was good. Maybe not very legible, but that was a good map of the relationship and those dependency trees. And so that was what we were doing. And then why? What is the takeaway? What do we try to use this for? So we want to enable everybody to document your reality. Not what you think reality is, but what do the systems actually say they are talking to? So many times we would go into an incident and it would be like, hey, well, that service doesn't use this as a service. When in reality, there had been some code change. It hadn't made it into the tribal knowledge. And we hadn't been able to learn that this was now a linkage through that. And the other piece was, if we wanted to do some analysis on where's our reliability hotspots, where are performance bottlenecks, things of those questions of that nature, we need this type of documented reality, not what we expect it to be. And that analysis, we're just trying to drive some impact, right? We want to actually make it more reliable, and we want to focus on the real reliability weaknesses, cost weaknesses, performance, whatever they might be. And the learning, we want to enable people to make faster, better decisions. And so now we have a graph on the back end. These are human readable relationships. So application A depends on a resource. All right, that's something you can explain to somebody. Doesn't matter if it's port 3306. They don't care. They just want to know it relies on that database. We can render it in a more flexible manner. That's very nice. And since it's a database, you can actually run queries against it and get subsections of this data, whatever you might be interested in. And so as we go through this talk here, Patrick's going to take over here in a second. Who's going to talk about how Astrolabe actually works to gather this data. Ryland is going to talk about the data representation, how we work with the graph database. And then we'll come back and we'll do a couple of little demos. We'll show you actually walking the environment. And we will show you how you can take this data, apply some of your own knowledge to it, and use things like Claude or ChatGPT to find some insights out of your environment. And so with that, let me hand it over to Patrick to talk about the guts of Astrolabe.
Awesome. Thanks, Chris. And we just had somebody ask about posting a link to the GitHub in the chat. So maybe if Ryland or Chris, you could do that for them while I'm talking, that'd be great. Yeah, so I'm super excited to get a chance to talk about this fun little tool we've been working on. So I'll talk about a few things. Really appreciate, Chris, you taking us through the backstory and the application, the use case. A few things I want to talk about is like who is it for, like who it's for right now, who's a usable audience for this tool, although we do have a roadmap, who's going to be able to use it right now. And then a little bit of how does it work under the hood. So if you go to the next slide, Chris.
Yes, there we go. Sorry.
So like there are users for this tool in the future as we get more robust with it. The first use case user for sure is, are you a DevOps engineer? Are you an SRE? Are you a developer? Are you somebody who remembers that one MySQL proxy command, that one Kubernetes command, that one pod exec command to figure things out about what's going on in your environment? The kind of catchphrase we've come up with for this tool is, you know, that library of scripts that you have sitting off on the side somewhere that you cycle through in your control R. This is what that's for. You take those library of scripts, you put it into Astrolabe, you codify that tribal knowledge and make it into a tool that's not only useful for you, but for other people to use. We're going to be, this is the classic toil reduction, removal of human error, less mistakes. So really, yeah, who's going to pick this up and go get the GitHub repo now is definitely going to be developers and SREs and DevOps engineers. Next slide, Chris.
Profile strategies.
Yeah, thank you.
Yep.
So what is at the core of that capability of Astrolabe to, it's like maybe one of the little secret sauces is, like Chris maybe will touch on or more has touched on more, is that this is agentless. This is not an agent that you install. So there's a little magic that comes with that, which is like, how does this tool know about your environment if you're not installing an agent? Well, basically we're giving the tool access to run some various commands in your environment, such as netstat. Could be any command that you want to give access to introspect your environment, but a basic one we have built out of the box is scraping connections off of netstat. So whereas as an engineer, you might log in and type that classic netstat PLANT and get some data out of it, you're going to put that script inside of a YAML file, put a little metadata on where that's used in your infrastructure, and then let the tool run that against all kinds of nodes. As you can see here, like on the left, you might be running this MySQL proxy. On the right, you're going to codify it a little more, massage the output in a format that Astrolabe can read, and then we're going to go from there. Next slide, Chris. So there's actually several ways that we're going to be able to, that with Astrolabe, you can customize the tool for your environment. That first layer that I just went over is profile strategies, super easy. All you have to do is write YAML files with bash scripts that are going to execute in a remote environment and plug it in and let it go. The second level is getting a little more hands-on, is going to be writing plugins to work with Astrolabe. The plugins that we have defined something called a provider, which can be thought of as a compute provider, access to compute resources, or really any infrastructure components. I've just kind of outlined here what the basic interface is on these plugins. Is you're providing Astrolabe with access to make connections to these resources, to profile these resources and return well-known data structures. And just on the left is an example of how we've written a Kubernetes provider, which exposes a profile API, just behind the scenes turns around and hits that Kubernetes API and returns the data in a structured format. So really, what is Astrolabe doing? You see for these various ways of letting introspect your environment is we're writing down all the various ways in code or in YAML that we can find connections in your environment and then let it go. It's like much like a web crawler, except for in web pages, there's one way to connect pages. We have, as we know, so many different ways. So what the tool is about is codifying all those different ways that things can be configured. All right, next slide, Chris. Which brings us to Neo4j. Like originally, this tool as a project had been written using an in-memory tree, nested recursive tree data structure, which works quite well for discovery. For like, okay, it works the way that discovery and web crawlers work, in that you kind of loop and go and loop and go. Aside from memory constraints, it works very well. But it does not work very well for a couple of things. It doesn't work well for exporting that data in other formats. It doesn't work well for visualizing the data in a way that lines up with the reality of the connections. In a tree, you have relationships that are only basically two-dimensional. In the graph, they can be multi-dimensional. And then the other thing is idempotency. Like this, really having it in a graph-based database allows us to enrich the database. So we were really super excited to rewrite Astrolabe for the open source release using Neo4j, kind of bring it all together as a tool that's open source and pluggable to run on Neo4j to represent and discover your cloud environment. And I think we're going to hand it off to Ryland now to talk a little bit more about that database integration and what we found out.
Yep. All right. So using a graph database was a pretty natural thing for us to want to do. Networks are already graphs, and so we're able to represent them in Neo4j by our vertices. They're going to be the infrastructure components, things like servers, clusters, load balancers, that kind of thing. And then our edges are going to be the relationships between those infrastructure components. And the edges are able to represent more than just network connections. We can also represent more just types of logical relationships or abstract relationships, such as like an application running on a server and that kind of thing. And then Neo4j was also just a very helpful development tool because it has interactive things like the Cypher query language and the UI that it comes with. So as we're developing, we're able to interact with the data that we were working with. And then next slide. And so,
out of order.
Yeah. So
there you go.
The way that we implemented Neo4j into our code base was we used the Neo model library, which is Neo4j's OGM. So it's the way for us to use the database in an object-oriented programming type of way. So this again just kind of fits with the infrastructure paradigm that we're working with, and so each one of our Python classes is representative of a type of infrastructure component, and this is just helpful for the way that we're thinking about it, and then also we're able to leverage some of the advantages of object-oriented programming. So, like for example, we were using some inheritance during this project. And then next slide. And so then when it came to working with the database, we were working with a mixture of the Neo model queries and the Cypher queries. Typically, we tried to stick with the Neo model queries just because that was the paradigm we're using. But there were certain times where doing Cypher queries made more sense. For example, if we were going to try to find some type of information that was independent of a specific type of class. So like if we wanted to find like an IP address somewhere, we can just query for that. And it worked very well integrating both these types of queries, and so they didn't interfere or anything like that. And then also it was very useful to just be working with a graph database just for the type of project that we're using, just because we can we can query things based off of just vertices or just edges, or we're able to like create certain schemas and different types of or like subsets. And so it was just it was a very useful tool for what we're trying to do. And then I'll pass it back on to Patrick for the demo.
All right, let me stop screen sharing on my side. And Patrick, take it away.
All right, so for the demo, kind of the first thing I wanted to do a little quick walkthrough of is really just to show what we're looking at. So we built like a little sandbox environment. Just have a few basic EC2 servers running here. And what we're looking at here is this application called Pineapple running on a couple different services. We just built a quick Python application, threw it up on some EC2 servers. We gave it databases. So there's two different flavors of this application running, 1 and 2, having their own respective databases. They have their own respective caches, Redis and Memcache. We also, just for fun, put it not only in EC2 on classic infrastructure, but we also put it in Kubernetes. So if you see kubectl is set up here locally, and we're able to actually see those. And that's one point to make about Astrolabe. At this point in the tool, it's very operator focused. So this is meant to be run from an operator's workstation or a dedicated like jump host or something that has privileged access to both a Kubernetes cluster and to AWS. And we do have plans to extend to other cloud providers and other container providers, stuff like that. The basic MVP out of the box here is working with Kubernetes and AWS. So you can see we have our little application running here. Once you have Astrolabe, which I'll just pop over here, we just published the open source repo, so you can go check that out. So you're going to clone that, install that as usual, and then you're going to try to run it, and it's not going to work because it's going to tell you you need to configure it. We won't do a full configuration here. I just want to show there's some basic things that are required. You have to tell it a little bit about how you tag your environments, what Kubernetes namespace to use, and how it can discover, using a remote execution of a command, what the name of a particular service or application is. Some basic constructs that you need to give it. And then maybe the most important thing is you need to give it a seed. We do have roadmap to get Astrolabe to just give it credentials and log into any of your systems and go. For right now, it requires you to tell it where to start. With one further ado, which is Neo4j on the back end, we have a basic little local setup here running. Just want to run this first. So we've got nothing in our Neo4j database now. So what we're going to do now is we're going to actually run Astrolabe. And like I said, operator focus is going to be very heavy on verbosity, so you can see what's going on. So just walk through that a little bit as it goes. What it does right away is it's just going to jump over and actually pre-inventory your environment before it even starts profiling nodes. Pull everything that it has that it cares about and put it in the database. And then it will seed the database with the seeds that we gave it and start profiling them. Profiling includes looking for connections, which it calls children in the log, looking for children, enriching data by reverse looking up IP addresses for various pieces of infrastructure, continuing to walk through and profile the whole environment. And here, as it's ended, we still have the classic output. This is the old tree data structure, which is super helpful for logging and just running it locally. But what's great for this conference, what we're really excited to present, is now if you run that same query in Neo4j, we're going to have this super rich environment here in the back end where we've detailed a bunch of different connections on. Here we have Pineapple 1 application, which uses the green resource databases and caches. We can see that this application has these compute nodes which power it. We can see that those compute nodes are part of a deployment and or an auto-scaling group, or in this case, a Kubernetes service. We could see the difference between our Kubernetes deployment and our EC2 deployment. And we can see the connection between them with the traffic controller, the load balancer. And that all just happened by basically taking, I'll jump over into the code for a second. All we did was basically take this codified YAML file, which says, here's how you look at connections. And we have a netstat that runs on machines that don't have netstat installed called notstat, which is a little joke for us. So just some very basic scraping of the environment, along with, there's some additional enriched profiling, like in code, we're actually telling it here how to profile a pod. So there's a little bit of code going on, but so much of this data has just come out of these like basic YAML files describing your connections. And again, what we have at the end of that is a pretty rich environment. And Chris is going to show you a little bit about what you can do with that. And I want to just demonstrate that we also, we can display that data in other formats too. So Astrolabe has built in the concept of outputting the data in different formats. So you can output in JSON, in GraphViz format. We're going to be building a Mermaid exporter. But there's so much you can do. We really see this as a jumping off point into really harnessing this power to like improve your environment, which is a perfect segue to Chris, who's going to show you one of our demos for what we want to do next with all this enriched data once we have it.
Yeah, and I think Roberto and Chet kind of guessed where we were going with this, because cost, performance, reliability, they're all very much intertwined. So as my screen loads here, there we go. So Claude, and you can see ran this ahead of time. I'm not going to tempt the live demo gods with 2 live demos in the same presentation. But this text blurb here, we'll set up the prompt, say, hey, Claude, you're a FinOps engineer, tasked with understanding cost and performance optimizations available in a cloud environment running on AWS. We tell it has a couple of applications, a relationship, and just so it doesn't hallucinate and get confused, we'll tell it what the ports are for. And then that honestly kind of ugly logging output, that's what this text blurb is right here. Right? So that's just a dump of the tree. And so if we click here, all right, Claude understood this. It wasn't able to give us a whole lot of insights yet, but it was able to understand the environment. But now what happens if we give it a little bit of information about these resources? These are all made up metrics just for a demo here, but say the cache CPU, P99, 45%. It's doing 1,800 requests per second. All right. Hopefully everybody can read this on the screen. And we'll do this for most of the resources there in Pineapple 1, but not yet Pineapple 2. And when we do that, this is what it comes back with. So now Claude is already starting to say, hey, these are some things that we can do based on what we've given to it, right? And so, it's got some cost impacts up here, like that might be 150K a year. This 35K a year. The version's also out of date. Oh, maybe you didn't realize that. If you didn't know that, is dump it in there. That's useful. Maybe not totally unique, but now it gets a little bit more interesting if I add Pineapple 2 stats to it. So this is the recommendations that I came with. And as Claude says, as soon as we give it Pineapple 2, this significantly changes the optimization strategy that it's going to recommend. And, one of the other things here that it identified is that if we say Pineapple 2 deals with 18,000 requests per second, and only 427 requests per second are coming from Pineapple 1, well, hey, you've got a load coming from somewhere else to understand. Now, a big load imbalance like that, you almost definitely know that already. But if you're not expecting that, it'd be a little surprising for you. And then it goes through here and it has changed a bunch of the recommendations going through there. Critical path optimizations, so you can prioritize them on what are, what are the kind of the top impacting ones. And if you give it more data, it can make better optimizations. Now, for this demo, we didn't try to do like full, curve reports or, other, detailed metrics, but you can, we've done it on other stuff where you can actually be very specific in the type of information that you feed along with these relationships, and very interesting things come back. And so, so that is absolutely, Roberto, you can get a lot of cost insight here and understanding. You could do the same thing and change it from dollars to latency, right? Or failure probabilities, and make all those same types of understandings from the map. All right, and so that is our demos. And kind of as a quick wrap up, I will click back over here. Love community contributions, right? So this is a new project. We are, just getting this off the ground. So easiest ways you can contribute if you're so inclined, profilers. Every environment has their snowflake. One of the magical things about Astrolabe, as Patrick mentions, you can encode that snowflake knowledge into these profilers or providers, depending on those, more likely profilers. Yeah, contribute one. Maybe you've got some other add-on, like you can provider or a visualization engine, FinOps tooling. That'd be amazing. And then always bug fixes. We're human. We make mistakes. Finding that there. Kind of the high level stuff. Patrick and Ryland both mentioned a couple of things that we're also, we have a laundry list of things we'd like to go build. One of those better user-defined profiling and relationships, make that just a little bit more user friendly. And then Patrick kind of alluded to this, supporting other cloud providers beyond AWS, both with API calls, but also things like Cloud Custodian, where maybe you can just seed a database with that, where you don't even have to necessarily directly call the API. So I think we are right at about time here. So if we're allowed, we will stick around and answer questions here.